Hello everyone, welcome to Brain Blitz Audios. Today in this episode of Mind Maps, we'll be dealing with the 14th chapter in the grade 12 syllabus for physics in CBSE. The name of this chapter is Semiconductor Electronics, and today we'll be using the help of this mind map in order to describe the chapter, Semiconductor Electronics, Materials, Devices, and Simple Circuits. So mind maps are very good ways for preparing for last minute exams. However, like this one, they can be very extensive, and therefore this video is devoted to describing this mind map in some detail. So let's begin. Semiconductor electronics. In electronic circuits, one of the most important aspects is the control of electron flow. Devices controlling electron flow are one of the basic building blocks of any circuit. Back in the early days, we used vacuum tubes until 1948. These tubes were big and they consumed high power and required high voltage. In this vacuum tubes, electrodes were placed in vacuum, which is present in the tubes, and the electron flow was controlled. These devices had limited life and low reliability, and they used to break down often. The next generation of electron controllers were semiconductors. These replaced tubes and were initiated, the first seed was initiated in the 1930s, and today we find semiconductors everywhere. These semiconductors require DC current in order to control electron flow. So in this chapter, we'll be looking at energy bands, the basics, and then aspects of each materials, conductors, semiconductors, and insulators. Then we'll be looking at the types of semiconductors, and finally some devices which are formed using semiconductors. So in order to understand how semiconductors work, we need to look at how electrons flow in matter. Now, materials are classified into three: conductors, insulators, and semiconductors. To know how electron flow happens, we should discuss conduction of electrons in a solid. Now, we've all studied Bohr's model of atom in the chapter Atoms. So in that, energy of electrons in an isolated atom is decided by the orbit. But when you have a collection of atoms, like in a solid, when atoms come together to form a solid, the orbitals and the atoms as a whole are close to each other. So therefore, the outer shells of each atom, they come very close to each other or can even overlap. So therefore, the conduction scenario here becomes very, very different. So solids, they form bands. Now, an energy band is basically a range of energies associated with the quantum states of electrons in a crystalline solid. These bands were discovered in 1927 by Walter Heitler and Fritz London. And energy bands are levels of energy in a solid with continuous energy variation. Now, in a conductor, insulator, or semiconductor, there are basically two types of bands: a valence band and a conduction band. Now, when the atoms come together, then what happens is that their valence shells, they are close to each other, and they sometimes overlap as well. So there they form a band called the valence band, the energy band, which are completely filled with electrons at 0 Kelvin. So valence bands are basically the bands which are formed by and includes every level of valence electrons. Now, in metallic solids, we have something called a metallic bond, where electrons are free to roam about in the solid. This is due to conduction bands. Conduction bands are basically the level of electrons which are out of the atoms, and they move freely within the electrons. So the bands with higher energy above the valence band are called the conduction band. Now, valence band and conduction band are two very different things, and sometimes they are separated by a band gap or forbidden gap. So this band gap is basically the gap between the top of the valence band and the bottom of the conduction band. As you can see, this is the energy gap. So this is the bottom of the conduction band, this is the top of the valence band, so the energy gap lies in between them. The presence or absence of an electron gap, an energy gap, determines the conductivity of a solid. So it is due to these gaps and bands that electricity flows through solids. And in the next section, we'll be looking at how conductors and insulators and also semiconductors are formed. So, classification of solids include conductors, metals, semiconductors, and insulators, and this is done on the basis of the band theory. So, in the band theory, it says that if there is no energy gap between the valence band and the conduction band, then there is basically no restriction for electrons from the valence band to move to the conduction band. So therefore the elements, the solids with least energy gap, which is 0 or maybe point values, they are the conductors. So in a conductor, there is a partially filled conduction band, and the valence band electrons move towards the conduction band, and the bands overlap. So therefore there is zero energy gap. So since there is zero energy gap, the density of charge carriers is very high in the conduction band for electrons. So in conductors, electrons are mainly the charge carriers, and sometimes holes can become charge carriers too. So 9 into 10 raised to 23 per meter cube holes are, so there are 9 into 10 raised to 23 holes per meter cube for a conductor. In case of copper, it's a special case, there are no holes, so it's 0 holes per meter cube. Let's look at the other end of the spectrum. What happens if you have a very high energy gap, say of the order 7 electron volts? You get insulators. Insulators have high energy gap and they have negligible hole density. So there is a huge gap between the valence band and conduction band, so the electrons, they need very high energy to move towards the conduction band, and which is highly unlikely. So most of the electrons still stay in the valence band and conduction of electricity is not possible. Now if we come to the middle between conductors and insulators, there are elements which have an energy gap between the valence band and conduction band, but the gap is small. So therefore with some impetus, you can actually make these materials conducting. And these kind of conductors are called semiconductors. Semiconductors have a low energy gap and they are partially conductive. The density of electrons is very low, and the energy gap lies in the order 0.72 for germanium and 1.1 electron volt for silicon. And again, the energy gap is between insulators and conductors. So for conductors, it's 0. For insulators, it's very high, but for semiconductors, it's not so high. Semiconductors with N-type have 7 into 10 raised to 15 holes per meter cube, and for 7 into 10 raised to and for p-type semiconductors, we have 1 into 10 raised to minus 9 holes per meter cube. Now the N-type and p-type will be discussed later. So this is how you can form conductors, semiconductors, and insulators. It's entirely dependent on the gap between the conduction band and the valence band. If there is no gap, like for example, if we can draw the valence band and conduction band, then it would be a bit clear. For conductors, it is basic. This is the conduction band, and the valence band will either be here, that means the gap is very low, or they can even overlap with the conduction band. So therefore, the energy gap is almost equal to 0. And that's why there is a lot of electrons flowing into the conduction band, which makes electricity conduction possible. For insulators, it's the opposite story. So as you can see, there is a huge energy difference between the conduction band and the valence band, and this is too much for electrons to cross, so they still stay in the valence band. And for semiconductors, the gap is actually narrow. It's narrow enough so that electrons can flow in the presence of impurities or in the presence of heat. So therefore, you can actually use semiconductors in special cases. And that's why semiconductors are very good at controlling the amount of electrons flowing. So now that we've studied the classification of solids into conductors, semiconductors, and insulators, and the reason why we do that, let's look and dive deep into semiconductors. So a semiconductor is a device which is used for controlling electron flow, and it is usually made with group 14 electrons. Group 14 elements. So we usually use group 14 elements such as silicon, germanium, etc. in order to make these kinds of conducting devices. So semiconductors are usually made with group 14 elements. Now, semiconductors as they are consist of a conduction band and a valence band, and they have some energy gap between them, some definite energy gap. Now, under normal circumstances, electrons cannot flow towards the conduction band. So in order for semiconductors to work, either you have to apply heat, or two, you have to put impurities. So one of these must happen. And accordingly, we have two types of semiconductors, intrinsic and extrinsic. In intrinsic semiconductors, we do not have any impurities. The semiconductor is pure silicon or germanium. So that means we apply heat in this scenario. So when you apply heat, there is a breaking of bonds, and therefore there's more electrons, and the electrons also have more energy with them. So therefore that energy is translated into motional energy, and therefore electrons move from valence band to conduction band. And also inside the conduction band you can have electrons breaking, and so conduction occurs. So when you have semiconductors, there is this unique phenomenon that occurs. So you have, say, an electron which is used in a bond between two silicon atoms. Under the heat that you give, so if you give heat to this silicon, the electron radiates out. And so when the electron radiates out, you actually get a positive space in the silicon atom where the electron used to be, and this space is called a hole, a semiconductor hole. These holes are also conductors of electricity. So in semiconductors, you have two agents of conduction. Electrons can conduct electricity, and also the positive holes. And these charge carriers have different concentrations in different kinds of semiconductors. For intrinsic semiconductors, the charge carrier concentration is the same. The number of electrons which are free in the semiconductor is equal to the number of holes present. And in semiconductors, the unique thing is that electrons move towards the positive end and the holes move towards the negative end. And they do this by an interesting phenomenon. So suppose we have two electrons here. What happens is that this electron gets, radiated out. So now you have a hole here. In order for this hole to move towards the other end, what happens is that the electron present here, the electron which is present here, now moves towards the hole, to this hole. So therefore technically the hole gets transferred from this side to this side. And that is how you can conduct holes. When the electrons, they try to fill up these spaces, they result in the hole getting transferred to the other end. So that is how you can form charge carriers, both electrons and holes. When it comes to current, the current is dictated by both the electrons and the holes. So the current I is equal to number of E times plus number of H. So the number of electrons plus the number of holes. So both electrons and holes produce current. Examples include silicon and germanium. Pure silicon and pure germanium are used as intrinsic semiconductors. What is the other type of semiconductor? The other type of semiconductor is extrinsic semiconductor. Now, we've learned that in semiconductors, you cannot use normal conditions. You have to heat the semiconductor up in order for conduction to occur. However, you can also, instead of applying heat, you can put in impurities. An extrinsic semiconductor is a semiconductor which is impure, or in the language of semiconductors, has doped. So what happens is that the silicon or germanium, which forms the semiconductor, is doped with another atom, another element. And according to the dope that is present, we have two types of semiconductors. So the dope can be electron rich, or it could be electron deficient. And accordingly, you can classify them as p-type semiconductors and n-type semiconductors. In p-type semiconductors, the silicon or germanium, which is group 14, is doped with trivalent elements. Trivalent elements refer to group 13, where they have an NP, where they have +3 configuration. So elements such as boron and aluminum are doped inside silicon. Now, the speciality here is that there occurs a lack of electrons. So when there is a lack of electrons in boron or aluminum, the electrons, they start flowing towards these spaces, the vacant spaces in boron and aluminum. And when that happens, the silicon atoms now have holes present. So the holes, in this case, become the majority carriers. Most of the current is transferred by the holes. And the electrons become minority carriers. So NH is greater than NE. The current still stays the same. It is NH plus NE, the number of holes plus the number of electrons. The current is dictated by the number of holes and the number of electrons. So this is how you form a p-type semiconductor. You essentially dope it with an electron deficient impurity, and then what happens is that the electrons move in, which leaves holes as the majority carriers in p-type semiconductors. The other end is when you dope the semiconductor with electron-rich impurities. This is where n-type semiconductors come in. Here, the silicon or germanium, it is doped with pentavalent elements. Pentavalent elements means +5 oxidation state, such as phosphorus, arsenic, antimony, etc. So all of these can be used as impurities. And the thing about here is that there is excess number of electrons. So there is an excess number of electrons here. So the electrons, they start moving in the conduction band and they form electricity. So therefore, electrons here are the majority carriers, and still some electrons are removed from the silicon. So therefore, holes are present as well as minority carriers. So in this scenario, the number of electrons, Ne, is greater than the number of holes, Nh. And once again, current is the sum of the number of electrons and the number of holes. So, now we've studied about the basic types of semiconductors. How are they used in a circuit? In a circuit, what we do is we form diodes. Now, earlier, we told you that the holes are the majority carriers for p-type. So therefore, since the holes are positive, the p-type semiconductor is generally positive. And the n-type semiconductor, since it has an excess of electrons, is generally negative. And what happens is that in order to form a regulator of electrons, we combine p-type and n-type semiconductors in order to form p-n junction. So a p-n junction is basically a junction formed by the combination of both p-type and n-type semiconductors. Now, a p-n junction is just purely made out of n-type and p-type semiconductors. Now, what happens if this p-n junction is capped? Now, the junction is capped by metallic surfaces on both ends. So the p-type gets covered by a metallic surface, and the n-type also gets covered by a metallic surface. Now, this scenario, the device that has this is called a semiconductor diode. A semiconductor diode is a p-n junction capped by metallic contacts at both ends. Now, these semiconductor diodes are essentially used in the circuits, and the circuits have a positive end and a negative end. So therefore, there are two ways in which you can connect semiconductor diodes. So this is the symbol for a diode, and this is the positive end, and this is the negative end. Now suppose if we connect the positive terminal of the battery to the positive part of the diode, and the negative terminal of the battery to the negative part of the diode, then you are essentially putting this diode in forward bias. Now, before we talk about forward and reverse bias, it's important to know how current flows to a p-n junction. Now, in the p-n junction, the p side has an excess number of holes, the n side has an excess number of electrons. So some of the electrons, they start moving towards the holes, and because of that activity, holes start moving towards the n-type as well. So the electrons move towards the p-type semiconductor, the holes move towards the n-type semiconductor. This phenomena of the motion of current is what we call diffusion current. So in diffusion current, the charge carrier gets diffused to the area with less concentration. Now, what happens is that as we have electrons flowing here, the holes flowing here and the electrons flowing there, then you get an excess of positive charge at one end and an excess of negative charge at the other end. So a thin layer is formed between the junction, in the junction between p-type and n-type semiconductors, and this layer is called as the depletion layer. The depletion layer does not allow any sort of current to pass through. Now, if you are connecting the diode to an external source, then what happens is that the increasing voltage, it disrupts the depletion layer. So since the depletion layer gets reduced, the transmission of charge carriers is possible once again, but this time due to the electric field, the external field. And that current, which is due to the external field, is called as the drift current. So in a semiconductor diode, you have two types of currents. One is the diffusion current and the other is the drift current. Both are essentially the movement of charged particles. The only difference is that drift current occurs in an electric field and diffusion current occurs naturally. So when a p-n junction is forward biased, the p part of the diode is connected to the positive end, and the n part of the diode is connected to the negative end. So the positive terminal is connected to the p side, negative terminal is connected to the n side. So therefore, the voltage now increases, and as the voltage increases, the depletion layer gets reduced. So there will be a very low depletion layer. So therefore, now the diffusion current, which earlier could not travel between these two, occurs. So the diffusion current increases. Now, what happens when you have reverse bias? In reverse bias, it's the exact opposite. The negative terminal of the battery is connected to the p side, and the positive terminal is connected to the n side. So what happens here? Over here, the voltage that increases now increases the depletion layer as well. So there is the resistance for electrons to flow now increases due to the change in polarity. So therefore, it is through this way that a diode controls the amount of electrons flowing through. If a diode is reverse biased, you cannot take current and make it pass through. But if it is a forward bias, current does flow through the diode. And that is how you can control control the electricity passing through the circuit. So therefore, a normal semiconductor diode is very, very important. Now, over the years, we have used diodes in various other aspects. One of the aspects here is what we call an LED. It is known as a light emitting diode. So in a light emitting diode, the semiconductor diode is forward biased. And when the diode is forward biased, current passes through the junction. And when current passes through the junction, the depletion layer slowly disintegrates. So how does it disintegrate? Well, at the depletion layer, more of the positive holes combine with the negative electrons. So when that happens, energy is released in the form of photons, and photons are basically light. So therefore, due to the decrease in the depletion layer, you get light. So light is emitted from a light emitting diode, and hence the name. Now, the second type of special semiconductor diode is what we call a photodiode. So while LEDs are used for TV, electronic gadgets, and even lighting, a photodiode is a PN junction whose function is controlled by the light allowed to fall on it. So what happens in a photodiode is that we have a semiconductor, and this semiconductor is reverse biased. So this is reverse biased. And the conductor is reversed biased, so therefore there is no current passing through here. So the depletion layer increases and there is no current passing through. But in a photodiode, now let's suppose this is a window over the depletion layer, and then you take light and make it incident on the photodiode, and it hits the depletion layer. So when it hits the depletion layer, there is combination between the positive holes and the negative electrons. And when that happens, current starts passing through for a short second. So as long as the light is incident, you can have current passing through the diode in reverse circuit, in the reverse bias. And that is why photodiodes are very important. These photodiodes are used as sensors, especially light sensors. So if you have a light sensor and if the light is incident, and then what happens is that due to the reverse bias, the current that is flowing through is detected. Now the whole reason is that during reverse bias, there is no current passing through. And so when the depletion layer hits, the depletion layer is hit by light energy, then there is passage of current, and that current can be measured. So that means you can sense that there is some light here. So through the circuit, we can actually use photodiodes as predominantly light sensors, and that's why they are in reverse bias, in order to function as a sensory instrument. Lastly, we have another important regulator called a Zener diode. This is used as a voltage regulator. So in a Zener diode, the diode is once again reverse biased. So positive, negative, and then we have negative end here and positive end here. But the speciality of a Zener diode is that the current flows even in reverse bias. So how is this achieved? A Zener diode is characterized by heavy doping. So there is a heavy amount of doping present in a Zener diode. And because of that, the P and N sides increase. The P and N sides are heavily doped, and therefore, because of heavy doping, there is a thin depletion layer. Now, when current passes through the reverse circuit, the reverse biased diode, what happens is that the current does not flow as the voltage increases until it reaches a specific value called the breakdown voltage. and after it reaches the breakdown voltage, current flows excessively. So when the current flows excessively, normal diodes get damaged. But a Zener diode is special is in the fact that since it has a thin depletion layer, since the depletion layer is thin, what happens is that it takes less amount of voltage to reach the breakdown voltage, and then you can have current passing through the heavily doped diode without any harm. So therefore, current passes through here in reverse bias as well. And why do you want a Zener diode to be kept in reverse bias? So, as we've looked into the current characteristics in forward and reverse bias, in reverse bias, a large amount of current passes through if the voltage is more than the breakdown voltage. And the large current is formed even when you have an insignificant change in delta V. So if delta V is very small, even then you have a large amount of current. So technically, you can consider the voltage of a Zener diode to be almost constant. So therefore, you can use a Zener diode as a voltage regulator. In order to give power to devices that need constant voltage, you can make this device as a voltage regulator. For forward bias, the current is normal. So as the voltage increases, the depletion layer starts gradually decreasing. So until it reaches a particular voltage, it does not conduct. After that, for some change in voltage, current is getting increased. And that is how current is conducted in a normal LED. For a Zener diode, it's the exact opposite, but once again, since the depletion layer is thin, current can pass through. And since the current can pass through, and since there is a significant change in voltage, you can use a Zener diode as a voltage regulator. So that is an overview about semiconductor electronics, materials, devices, and simple circuits. We looked at the history of semiconductors, the mechanism behind the conductivity of semiconductors, the various types of conducting material, that is conductors, semiconductors, and insulators. We looked at the various types of semiconductors, p-type, n-type, pure, doped, etc. Then we looked at diodes and how a diode is formed, how it passes current, what is the technical way in which the diodes are connected. Then we looked at special diodes such as LEDs, photodiodes, Zener diodes, etc. So we hope you found this chapter interesting. For more useful and informative mind maps, don't forget to click the link in the description down below. And you can also subscribe to our channel, Brain Blitz Audios, for more useful and interesting content such as Neet preparation, learner words, etc. So until the next webisode, take care, stay safe, bye-bye for now.